Hello everybody, welcome back to From Rhythm to Algorithm. This is part 2. This one is called The Infinite and the Infinitesimal. In this episode we're going to do a lot of math. We've set up our physical system or our physical theory very well, and now we're going to make just a couple, we're going to make a couple mathematical distinctions, solve a couple math problems, and discuss a couple already proven results and theorems that are already out there. So the first thing I want to make a distinct difference in is infinity is the concept. There's one concept of infinity, and most mathematicians know that. But if you're a lay person, you might hear you have an infinitely uncountable set, and a set that's infinite but countable. Two sets that are infinite, but I forget whatever one I just didn't say. Is uncountable or whatever. But I want to make the direct distinction at the basis of mathematics. There's one concept of zero and there's one concept of infinity. You can't measure infinity. Infinity is not a thing. Infinity is a concept. The infinitesimal, that's different. You can't measure the infinitesimal, but it's simply just the smallest anything can be, which is the electron. And when I was talking earlier about scale, measurement limits our knowledge about the universe. And past that, we can make definitive deductions, but we also need to point out it doesn't matter. Like if you can't, what I mean is below the Planck scale, if you start trying to ask questions, it's simply there's no way to approach that. And same thing with on the infinite scale. You can't ask meaningful questions. So the infinite and the infinitesimal give us bounds to our math system. And we're going to continue that with our Polygon argument. So here I just have written 1, 2, and then a triangle, square, and pentagon. So now ask yourself, what happens when we take the limit as n goes to infinity? What happens to these shapes as the number of sides approaches infinity? Well, you approach a circle with the radius of 1. And here I just have, again, tension points, which will soon be pressure points. I'll probably be the next episode, which, spoiler alert, you have joints, you have discrete parts, they're all combined into one system. That's what you already call, oh, he hit me in a pressure point, a weak spot. That's really how you unify the forces. Every force is exerted on a surface area is a pressure. Getting back to math, you approach a circle with the radius of 1. And that is literally the physical derivation of the unit circle. This is where all of your trigonomic relations come from. I didn't even say it on the first part I had a dimensionless quantity is a scalar. That is why your unit circle and basically any real mathematical calculations you're using radians is because radians is a dimensionless quantity. And so that's the mathematical argument. Now, remember one was to be something physical? Well, one radius of the electron. Because how do we know that? Well, the electron, right now in particle physics, out of all of the measurements we've ever taken, every physicist says it has no internal structure. So we know it's the smallest thing that can be considered. And it is. And past that, the smallest molecule you have is the hydrogen atom. And I'm not going to go through, that's completely consistent with cosmological evolution. But up here, so now that we've bounded that, now I want to talk about what I said, locality is relative to scale. If you go outside right now, you can look directly into the sun if you'd like, but you can't really discern, or you can't resolve the light, it'd be too much information. But you would just see a sphere. But if you got really close to the sun, you would see hot gas spewing out over there. And this is something you can do with telescopes, not homemade telescopes, but non-professionals can do these things. And so, if this was true, you'd be able to see this regardless of scale. And you can. What I have up here, I'll just take the picture off and bring it up to the camera. Right here is a picture of the picture of a black hole. And this was just recent, I don't know exactly when, but pretty recent. Picture of a black hole, and that is the largest structure we have access to. And now here's the smallest. Here is a picture from a scanning electron telescope about a hydrogen atom. If I can get this off here without ruining it. There is a picture of the hydrogen atom. And these are measurements, right? You take a physical thing, you interact with it some way, and you get a picture. And what can we see from both of these? You can visually see the tension points on these bad boys. You can see them. It's the same thing. Look at the shadow in the room. You can literally see layers to it. There's discrete layers, and then there's just some middle ground. But you can definitely see differences. And I'll get into that on a different, maybe this episode, but that's more mathematics. And so, regardless of how big, don't think of a black hole as a black hole. Think of a black hole as just a humongously large particle. And we can do that. We already know that from the no-hair theorem. And that simply states that all black holes can be described by three properties: mass, charge, and angular momentum. And past that, they're all indistinguishable. Same with electrons. And so what that does is that really bounds our entire physical knowledge completely. And the final thing for the next clip is, what predictions does this analysis make? And I have up here written efficiency. Well, efficiency is proportional, or efficiency proportions regardless of scale. And what I mean by that is, whether you're talking about really small things or really big things, the relative size is what matters. You would expect there to be the same type of proportions, whether you're talking about really small systems or very big systems. And now we're going to see how this directly brings realistic insight to dark energy. And also, now we're going to talk about some of those other math theorems I was saying. So now that we've built all of that mathematics and set the physical foundations, now what we can do is we can ask a very specific question about efficiency. Over the large-scale evolution of the universe and over the very large but less large evolution of biology, we can make the very simple statement that things want to be efficient. And on the last slide we said we'd be able to see those proportions in physical systems, and that's what we're going to do. So at first I want you to ask yourself, imagine you're packing the trunk for a family trip. How do you be most efficient? Well, very simply, you just arrange the shapes of your suitcases and your bags and your luggage to take up as much volume of the trunk as you can. When you do that, you have boxes and objects of different shapes and sizes and blah blah blah. What we just showed on the last slide, mathematically proved, is that effectively, regardless, like I can see the shape of the light post, it's different. There's a cylinder-like, this is a square-like, or a rectangle-like. But on the basic fundamental level, basically everything's a sphere. And so now instead of imagining you're packing a trunk for a family trip, imagine you simply just have a box and you want to put as many golf balls in the box as you can. How do you do it most efficiently? Well, if you order them like this, you get a percentage of about 74%. Of the volume of the box is occupied by the volume of the balls. If you just throw it in there without anything, you get an average percentage of 64%. And so, if that were true, that you could view most particles simply as a sphere, you would expect to see extremely, like I said, the same proportions over extremely different types of systems. And so, as a stated fact, the ratio of glial cells to neurons in your brain is 1 to 3.76. For each neuron, and this does vary, but this is, for one neuron, you have 3.76 glial cells, and that's in your cortex. I put a -1 up there because that is the inverse of the cerebellum. The cerebellum is the older part of your brain, the cortex the newer. So, and that percentage comes out to 74%. We put balls in a box, we got 74% of the volume occupied. We look at our brain, we get the same number. And now, you have this thing in physics, this big conundrum. What is dark energy? We'll get into dark matter a little bit differently, but dark energy is for sure nothing. Well, dark matter is for sure nothing as well, but this is why dark energy is nothing. If you simply view the time since this cosmological microwave background till now as a very short period of time, which it is, you would expect the efficiency to go up. That's exactly what we see in the Hubble constant. The SHUS, and this is an acronym, SHUS it's an acronym for some organization or project, I don't know what it stands for, but the rate that it gives is 74 kilometers per second per megaparsec. And the cosmological microwave background value measurement gives 67.4 kilometers per second per megaparsec. It's all the same thing. It's all physical systems trying to be more efficient. And because the relative scale, the distance between galaxies is so huge, they all look like point sources when you go out and look up in the sky. This is them scaling from your brain to galaxies across the universe. And I do a lot of mathematics. This is actually probably one of the coolest results I've ever personally realized. And if you look at, here's just the picture, I wrote the galaxy, but this is a map of the universe, a simulation of the universe. And here's a simulation of the neurons in the brain. They're exactly the same. And so, this is the true solution to what is dark energy. Dark energy is an inefficiency of a physical system moving towards an efficient state. And now, I'm going to cover one, this will probably be the end of this episode, but now what we're going to do is we're going to take this result and we're going to integrate it with the concept of tension, and we're going to build tension path physics. But this is the coolest result I've ever figured out. That's that.